All right, so we're going to talk today about a moment resulting from what's called a couple. And a couple is just two forces equal in magnitude and opposite in direction. So this is a couple. There's two vectors equal opposite magnitude. In other words, the magnitude is the same, equal magnitude, but opposite directions. Equal magnitude, opposite direction. And I think you can understand if we apply them, let's say we have some kind of arbitrary shape structure, and we're applying these vectors, this one here and that one there, it's going to cause a rotation, right? This is like a shear, and you're going to have a rotation. In this case, it's going to be in this direction, which is a positive moment. So if we wanted to evaluate the magnitude of that moment, let's say we want to evaluate the magnitude of that moment at a location here. It could be any arbitrary moment, but this one is easier to evaluate. If the distance, the perpendicular distance, that's the perpendicular distance, right? Meaning it's the distance, basically the shortest distance between two lines, two parallel lines. And we're going to call that D. And we want to evaluate the moment here. We'd say that the moment 0, and I'm going to give these names. I'll call that one F, and I'll call this one negative F, because it's going off in the other direction. Basically the same vector, going off in different directions. The moment caused by this vector at that point, right, the line of action is going right through the point. So the moment arm essentially has a 0 length. So that moment is 0. And the moment caused by this vector is a F, a force in this direction. I know I wrote negative, but trust me, it's a force in that direction, a magnitude. We're doing these as just magnitudes times D. So the magnitude of my moment vector, and remember a moment is not a scalar, it's a vector. But the magnitude of M0 equals simply F times D. Okay, then you can do that. So that's kind of in planar space. We can do kind of a general result. And I'm going to draw this a little differently. And the other thing I want to point, so one more thing I wanted to point out about a couple, which is because the forces are in the opposite direction, there's no the net force. In other words, if you add up the net force of the two vectors, essentially is 0. So if we added these two vectors, if I called one FA and the other FB, and knowing they're equal and opposite magnitude, FA plus FB equals 0, which is, you're going like, wow, it's not really doing anything, and it's not doing anything in terms of pushing it in the X direction or pushing it in the Y direction, but it is causing this thing to rotate or spin around some axis, all right? So what if we want to evaluate this thing sort of in a general three-dimensional, and I'm going to draw a 3D vector down here. So I'm going to draw my couple here. Make sure, let me use the same way I did it in my notes. I'm going to have one going this way, the other one going this way. So we're not in the XY, we're in a kind of we're in an XYZ world. And this is sort of up, not on the XY plane, but it's somewhere up here. We've applied this we have a couple, and these forces are, I'm going to call one FA, and we'll call the other one FB. Which one do I want FA and which one be FB? I'll call this one FA. This one we're going to call FB. Remembering that FA is just equal to the negative of FB. And what we want to do is calculate the moment about any arbitrary point O. So I'll put an arbitrary point O down here. I don't know where it is. Maybe it's in the XY plane, but it might be in the Z, negative Z value. And remember that we calculate the moment equal to R cross F, where we take R basically from our moment, the point, the position, or the point where we're evaluating the moment to somewhere on the line of action. So I'm going to do that. I'm going to draw a R vector here. This will be RA. And I'm going to draw RB here. All right, that's my RB. And I can define another vector, which I'm going to call RAB, which will go right here, RAB. And I think we can see that RA plus RAB is just going to be equal to RB. But let's write out the moment caused by the couple, and then we'll look and you'll see it has kind of an interesting result that we're going to get. So the moment is going to be equal to RA cross FA, right? So that we have the moment at this point caused by this vector, caused by that force vector. And then we're going to add to it RB cross FB. And what we can do is we can substitute in just F prime, because basically FA equals negative FB. So we're going to end up with RA cross F, I'll just call it F, plus RB cross F. Oh, I need a negative sign here, because one of them, this one I'm going to say, is going in the other direction, right? Because they're equal and opposite. They're equal, but in the opposite direction. So we can just apply a negative to it, and we'll have FA and FB, basically just calling them F. And we can basically, this is like cross product multiplication. You can like do distribution and other sort of same kind of processes you do with regular multiplication. So I can say RA minus RB in parentheses cross F. See, all I did was take the F out, and then write in the parentheses RA minus RB. And we know, and I already kind of said it over here, which is that RA plus RAB equals RB. Right? We can do that by the triangle rule. So you're taking from this point a vector to here, here to here, and it's going to be equal to a vector going from that same original point to the end point of that second vector. That's the triangle rule. So now we can define RA minus RB equals negative RAB. RA minus RB equals negative RAB. I kind of wish I had defined them the other way. Negative RAB. So you're going to end up with a moment equals negative RAB cross F. Right? Because all I did is I took this value, RA minus RB, I substitute negative RAB, like I had here, cross F. So this is the moment. The moment is going to be equal to a vector from one side to the other, anywhere on the line of action of either of these forces, and crossed with the force vector F. And the interesting thing about this is I did not define this point right here. I could have done the same thing from some other point here, right? The result has nothing to do with the original point that we're evaluating the moment at. If we had evaluated the moment from this point, and I had drawn the same analysis, and I had drawn all these position vectors, like from here to here and here to here, you see you end up with the same RAB, which is like here. So the interesting thing is that the moment caused by a couple does not depend on where you're evaluating the moment. And it's kind of an odd thing, but it's odd but true, and it's what we call, it is a vector, and we call that a free vector. A free vector, which means that we can apply the moment anywhere on that object. So we have a couple like this one. I can say this moment could be at that location, O, and it also causes a moment, the same magnitude moment, at any other location on that object. So it's a free vector, and that's going to be very useful when we get to simplifying systems and are looking at the moments caused by couples and figuring out the total moment when we're summing up the moments. And in a minute, you're going to, later on when we get to our next lectures, we'll talk about what I mean by summing up moments and why we do that. And that's basically it. So keep in mind that a moment caused by a couple is a free vector, and it's applied anywhere on the object. So if you have a system like this, again, this is my wall. Here I have a beam, and I apply a couple here. That value can be applied at any point along the beam. And that'll be important when we're adding that to another force. Here's a force, a single force, causing a moment, and we can evaluate the moment of that force like here, like we did before, and then add it to that free vector, because that free vector is applicable anywhere. So that's it, kind of an odd result. This is a couple, the moment resulting from a couple. So next we're going to look at simplifying systems, and that's why I was kind of showing this here before, because we're going to take like systems where you have a bunch of forces on it, like a couple, a force, and maybe some other forces, and we're going to simplify them and express them with fewer number of forces and moments, or even maybe just one force in some cases. So that is it for today. If you have any questions, send me an email. Otherwise, I'm going to see you in class.